Well, welcome everybody. I'm Nate Snydecki. This is our Mechanical Engineering Department seminar, and this is our second talk on our Mechanical Engineering for Space lectures. I won't introduce our speaker. I'll let our communications director, Andy Freeberg, introduce our speaker today. Andy, do you want to take it away? But before I do have you do the introduction, just some ground rules before we start. Our speaker will present and we'll have at the end a Q&A session where he'll be able to answer your questions. So if you like during the talk, you can write your questions in the chat, or you can save it until the end and we can use either the raise hand feature or you can unmute yourself. But for now, I think I'll pass it back to Andy to introduce our speaker.
Thanks, Nate. Yeah, so I appreciate this is fun for me. Today's speaker, Travis Lange, comes from my former institution, the SLAC National Accelerator Laboratory at Stanford University. And so for those who aren't familiar with SLAC, it's a place that has a really cool history. Back in the 60s and 70s, SLAC is where physicists first did collision experiments that confirm protons and neutrons are made up of these smaller constituent particles that we call quarks. And even though the lab doesn't collide particles anymore, it still does a ton of the same kind of cutting edge physics and other science experiments. And they all kind of carry this same formula of scientists working really closely with engineers on just some of the world's most ambitious research experiments and facilities. And so at the center of these experiments, there's always some sort of advanced sensor or detector or that kind of thing that's going to read out the experimental data. And so for several decades, SLAC has been a place where detector design and fabrication is a core competency of the lab. And so that brings me to Travis's project, the LSST camera. And when I was at SLAC, this was one of my favorite projects to follow. And so when Nate was looking for speakers for the seminar series this fall, I was really excited to get somebody from LSST to come talk to our department here. For what it's worth, I started at SLAC in 2011, and at that point, they had already been working on LSST for over 10 years. And so for what Travis is going to tell you about is really the culmination of more than 20 years of focused development. And it's really at a pretty exciting point right now, as you'll learn. So I will not go into more details. I'll let Travis do that, but let me introduce Travis first. Another thing I have in common with Travis, we're both from Minnesota. Travis has a degree in physics from Gustavus Adolphus College and mechanical engineering from the University of Minnesota. While completing his mechanical engineering degree, he was also the lead mechanical engineer and project manager for University of Minnesota's solar vehicle project. Travis then spent about 12 years developing an extremely high energy short pulse laser for another very big, ambitious science project located in the Bay Area, the National Ignition Facility at Lawrence Livermore National Lab. Travis joined the Rubin LSST Camera team at SLAC in October 2014, so I guess 6 years ago this month, and is currently acting as the lead mechanical engineer for the integration and test team there. And in that role, he leads technical planning for everything related to the assembling and testing of the camera. And with that, I'll hand it off to you, Travis. Thank you so much for being here and doing this.
Thanks, Andy, and thanks, Nate, as well. So yeah, I guess that was a pretty good intro to who I am, what I've been working on over the past, I guess I'll say about 20 years. So I have a couple pictures that are part of that same intro. As Andy mentioned, I am from Minnesota, so I don't typically have much of my Minnesota accent left, but there's occasionally I'll slip in something that like the oofta, or yeah, there you go. Oh, okay. All right. So occasionally I'll slip in the little oofta or Minnesota Fargo speak. So my early career was in precision engineering, actually. So I worked in a place that made some custom air bearings. So we made a lot of air bearings, stages, spindles, that sort of thing. That was kind of my foray into real precise motion of mechanical systems. As Andy mentioned, I spent a couple of years working on this solar car. So here's our solar car cruising along at 80 miles an hour during a test outside of Minneapolis. The race that we designed this car for actually started at the Indianapolis Motor Speedway. So this is actually a test run at the Indy Speedway. The starting line. Pretty fun to say that I actually drove on the Brickyard, and in a car like this, you actually do feel the 4 bricks that you cross over at the start and finish line. So it was pretty exciting. The big laser project that Andy alluded to, this ARC, this advanced radiographic capability, it's a very high energy short pulse laser. So that was kind of a cradle to grave design, analysis, installation, test that I was involved with that project. We had to figure out how to stuff this into a facility that had already been designed for the National Ignition Facility, and we actually redirected a full quad, or 4 of these very large beams. To give you a sense of scale, this is this ball here is 10 meters in diameter. This chamber right here, it says compressor vessel 1. That is, it's roughly 10 feet across and 20 feet long, and that was a vacuum chamber that was in the 10 to the minus 5 torr region. So not extremely high vacuum, but still nonetheless a large vacuum chamber. And there were 2 of those. Looking inside that big compressor vessel, this is actually a picture inside. You can see the scale of some of those optics. So I worked on, both the design of the chamber itself and these the mounts for all these optics. These are actually gratings, diffraction gratings for spreading the colors of the beam. And for the past 6 years, I've been working on the LSST camera. So what is the Vera Rubin Observatory? Well, it's a ground-based, U.S.-funded telescope located in northern Chile. And it's a survey telescope, meaning that it's going to look at the entire night sky. And it will do that repeatedly every night for 10 years. And when it does that, it's going to map out a dynamic, the dynamic universe, essentially. So how things move with respect to one another over time. So there are some people who are looking at things like the near-Earth objects and tracking of those things. But predominantly, most people are really interested in how this can be used to help us understand the basic fundamental nature of dark energy and dark matter. By understanding how light bends as it translates through space. So this is a big project. It has a lot of superlatives. It's an 8-meter primary mirror that focuses the light into the camera. The camera itself is 3.2 gigapixels, so that's the largest set of CCDs ever put together. In fact, actually, we're going through the process right now of getting certified by the Guinness Book. So in 2021, this camera will be in the Guinness Book of Records as the biggest digital camera. So one of the really interesting things about how this camera is going to operate is it will take an image, and within 2 seconds it reads out the image, and it processes the data into a bunch of software, and that software is going to parse it into data products. When I say data products, I mean that means when people are looking for specific events in space. So if you're looking at supernova formation, or if you want to see weak lensing, for instance, those are a couple of features that certain scientists might be interested in. So it'll parse up the image into a bunch of data products, and then it will store all that data into a data center located somewhere in the United States. That's ongoing right now. And within 60 seconds of the shutter closing on the camera, it's actually going to send an alert to anybody who's interested. So it will send a real-time alert to anyone who's interested, including citizen scientists. So if you're interested in being a citizen scientist, you too can sign up for one of these alerts, and you get an alert on your text on your phone, and you can take your own microscope or telescope and train it to whatever coordinate it says to look. So that's pretty exciting. The focal plane itself, it's 640 millimeters across, so it's a very large array of CCDs. It has a flatness requirement of 20 microns peak to valley across every point of that surface. That's a really difficult thing to do. I'll talk about that a little bit more later on. how deep it can see. So as I mentioned, it's a survey telescope, so it's not intended to be something that sees very deep into space, although it can see fairly deep. So it sees like 24th magnitude. That's not quite as good as something like the Hubble. The Hubble is 27th, 28th magnitude. But when you take a bunch of images and you overlay them over the course of the 10 years, you get up to about 1,000 images in the same location in space. And when you do that, you will actually get the ability to see it more like in the 27th magnitude, which is that's a pretty deep image. Just for reference, 5th magnitude is about as good as a human eye can ever do, and that's even a bit of a stretch. So 10 years of the project, it's going to collect like 5 million images, 37 billion objects, 7 trillion light sources, and then tens of billions of time domain events, which will be the alerts that will be sent out and distributed. As you can imagine, working on something like this is not simple, and it takes a lot of dedication and a lot of folks that are working on it together. So it's a big collaboration. This is just for the camera, not for the entire telescope project, the observatory project. So at SLAC, we are the main management of the camera, and we actually are doing all the integration of the camera, and also housed a lot of the design of many elements of the camera itself. Some of the elements that we did not do the design of on our own are the main optics, so the big lenses. I'll talk about those a little bit later on. Lawrence Livermore actually handled the procurement and design of those optics. Brookhaven National Lab out in Long Island did the design of the sensor assemblies for us. And then we have a partner institution in France, IN2P3, and they are mostly responsible for handling the mechanical design of the filter exchange system. Talk about that a little bit more, and a lot of sensor level testing. And then we have a lot of universities who are also big partners in what we are doing. I don't have the University of Washington on here. I apologize. That's actually a big part of the observatory itself. It's not actually a big part of the camera. So as Andy mentioned, this has been taking a very long time. So if anybody is ever getting involved in a research project like this, get ready to spend half your life dedicated to making this become a reality. So one of the very early idea that Tony Tyson, the chief scientist, formed the idea in 1999, so a very long time ago. There were already early design concepts by 2005. And as Andy mentioned, in 2011, we actually had the very first approved mission for this camera. And in 2015, we actually got the approval to start the construction. And our finish date was supposed to be 2020. Both COVID and some technical challenges have delayed that a little bit. Right now, we're looking probably at the end of 2021 when we close out the project and ship it to Chile. So here's a brief overview of the camera with a 3/4 cut section out of it. This red section in the middle, and actually, can you guys see my cursor when I move my cursor? Andy? Yes. Okay, thank you. So the cursor here, this red is the cryostat. So the cryostat is what houses all of the CCDs and the readout and digitization electronics for those CCDs. And we have in front of that is the third corrector optic, the L3 lens, which is also a vacuum barrier. In front of that is a filter. So we actually have 5 onboard colored filters, so we can change the different wavelengths of light that actually get to the sensors. We actually have 6 total of those filters, but only 5 on board at any given time. In the front is an inseparable pair of large corrector optics. And in the back, we have back here this utility trunk, which houses all of all the power supplies and computers and readout electronics for the entire camera. So let's go through this fairly quickly so we don't spend too much time on this, but this is the camera exploded into view. So we start with the 4K by 4K sensors. We assemble those onto a Science Raft tower module that is a 3x3 array. So there's actually 9 of those sensors on this Raft tower module, and that gets installed into the cryostat. I'm going to talk about that a bit more in detail a little bit later. We also have 4 of these corner Raft modules. They actually have intrafocal and extrafocal sensors, so we can use them for wavefront sensing. And those also go in the cryostat. I mentioned the L3 lens, these 6 filters, but only 5 are on the camera at any given time. And we have this filter exchange system. So this carousel of filters rotates, and then we exchange a filter from this stored location into an online position in front of the L3 lens. Main camera body, just to keep everything housed and clean. In the front, we have this L1, L2 lens assembly. We have a large shutter, which I'll talk about a little bit later. And the back is that utility trunk, which I mentioned. So, you know, this thing is a large camera. So it's definitely, it has a big focal array of CCDs. But one of the things that, you know, it's hard to imagine a camera of 5.5 feet in diameter by 12 feet long. So, you know, it's if I were to do something equivalent sized, it's about the size of a small car in physical size, but it's a little bit more dense than a small car. So at 6,600 pounds, it's a little bit more like a really large cargo van. But what's really impressive is that even if that seems pretty large for a camera, it's actually very small compared to the telescope at large. So this assembly right here is the telescope mount assembly. It's what rotates this axis. There's a vertical axis that it rotates, and then there's another elevation axis that goes through here. The camera is this represented by this yellow steel counterweight that's up there currently. And use that for testing. But you can imagine that the camera itself is quite large, but it's very small compared to the rest of the telescope. This is actually what the telescope looks like today. It's not quite completed itself. We're still working on the dome, but you can see to scale how large it is by some of the cars that are located in the bottom. So the camera's resolution, it's the 3.2 billion pixels. It's a lot more than your little iPhone can do. And you know, if we were going to try to display the LSST camera on full-size raw images, you know, each sensor is 4K by 4K, and there are 189 of them. And you know, 4K TVs are not actually 4K by 4K because they're widescreen, so they're actually 2K by 4K. So you need 2 of them per sensor. So if you were gonna display one sensor, you're looking at 2 large TVs. And if you wanted one of those rafts, you're looking at 9 of these TVs. And if you are trying to do the entire array of CCDs, you're looking at 378 of these 4K TVs, which is roughly the size of half of a basketball court. So it's very large images that are being generated by this camera. I mentioned the focal plane flatness briefly. So that 640 millimeter focal plane flat to 20 microns, it's a little hard to judge how flat that really is. So making an analogy of how flat that is, if you had the entire US would have to be flat to like 480 feet total. So it's maybe gives a little bit better idea of how flat the focal plane needs to be. And the reason for that is that it's very fast focusing optics because of the wide field of view. And if we don't have them all contained within a narrow band of the same focal plane, we're gonna have problems with the consistency of focus for the images. All right, I'm gonna take a quick break because I'm gonna close my window briefly. Apologize. Neighbor is mowing lawn. So I'm going to talk a little bit about the installing these Raft tower modules into the cryostat because that was one of the things that I spent a lot of my time on. So we had 21 of these Science Raft tower modules that had to get installed into the cryostat. And you can see they're roughly, a little over 2 feet tall, like half a meter tall. The base is 126 millimeters square. And when we put them into the cryostat, the edge of the CCD of the sensor that is being installed and the ones that might already be installed is only 500 microns. So that's roughly 4 hairs width between sensors. So it's a very small gap between these sensors, and they're extremely fragile and very expensive. Unfortunately, there's not a lot of detail for how we can handle them when we draw them into the cryostat. So we decided early on that we wanted to have the sensors always facing down during the integration process, just to minimize how much debris lands on the surfaces. They're not something we want to touch after they're all cleaned because of their fragility. So with them facing down, we won't have any of the dust and particulates landing on the sensor surfaces, which means there's only this back surface that we have to grab onto and to draw them into the cryostat. And in fact, actually, there's only 4 little tapped holes. So we had 4 little tapped holes, and the rods which could be attached to those could only be 6 millimeters in diameter because of all the other restrictions inside the cryostat. It was a very tight package. So essentially, the entire way when this starts entering the cryostat until it's fully seated, there's about a millimeter of clearance around any given area of this Raft tower assembly to the internal components of the cryostat. It's really difficult. If you've ever played Operation, it's like the ultimate game of Operation. Here is a picture of some early testing that we were doing, which you can kind of see some of the challenges we faced. So this is obviously just using my little iPhone to take a picture of the gap. But the gap that I'm referring to is between this sensor, which is already installed, and this one, which is being raised up onto these balls. So this assembly of sensors eventually gets mounted via a kinematic mount system. So there's 3 balls and 3 sets of V groove posts, which it lands on, and those are all just hard machined features with very tight tolerances on all those features. But before it lands on the kinematic mount, of course, this part is free to move back and forth. So that's the part that gets really challenging during installation. So, given that these things are like $3 million a piece, really we'd like to have a lot more clearance between the sensors. So this is a good example of what we'd actually prefer to have. But unfortunately, of course, what we really have is something that looks a little bit more like this, where if you scale it, it's about a ½ inch of clearance on each side of the car parked in between 2 adjacent cars. So the design that we ended up coming up with, and I apologize because I'm skipping over a whole lot of details on the challenges involved with installing the Raft into the cryostat for time reasons. But what we ended up coming up with in the design is this system right here. So there's a long draw vertical stage that holds this big carbon fiber arm that goes down all the way through the cryostat and attaches to the Raft tower module, which is shown here with a frame that's supporting the Raft tower module. So we lower this arm through, we attach it to the Raft tower module, take the frame support off, and now the thing is free to raise up into the cryostat. So this mechanism has a long vertical draw, which has to be very accurate. It also has an assembly right here that allows for a small 2 millimeter in each of these orthogonal directions, and a rotation. So there's actually a big rotation bearing in, so it can rotate as well. So we have 4 degrees of freedom within this mechanism to allow us to be able to drive this thing in position. And the rest of this, what's shown here, is a very large weldment which supports that cryostat independently. So the cryostat is supported in this big weldment. That red, you can see that red housing that's sticking down through the weldment, that's the cryostat itself. Again, shown with a little section. Some details. I think the other thing that was a little bit unique about what we did here is that I chose to use a granite base. I'd never used a granite base for a stage quite like this in the past, but the nice thing about a granite base is that you can get the surface very, very flat, which is great for these super precision THK rails. And not only flat, but you can get the surface flat and square to the base, which was another requirement that I had for maintaining the orthogonality of this entire system as it goes down through the cryostat. With any drift, with any pitch, roll, and yaw errors of this vertical stage, you can imagine that the boom is that this arm is 1 meter long. The raft itself is another ½ meter. So now you're talking about 1.5 meters from where the stage is attached to the stage. So pitch, roll, and yaw errors can cause a lot of motion at the end of that big long boom. And we just don't have clearance for that much motion. So that's why we had to have a very precision vertical stage for this process. One of the other things that we needed to do, since the clearance is just too tight to rely on human eyes to see the clearance between the raft that we're installing and the ones that are already installed, we actually designed a system of cameras and lenses. So we actually have 4 really large bitelecentric lenses attached to CCD cameras, looking up at the 4 corners of the raft tower that's being installed. And when we do that, we have something that kind of looks like this, where we look at these 4 corners, and if we look at this corner here, for instance, we can actually monitor this gap here. And we came up with some software where we actually had a region of interest here and here, and in that region of interest, we made a series of vertical lines or horizontal lines, and then measured the relative light intensity that the camera sees. And when you do that, you can actually detect where the edge of that sensor is using the software. So that's actually one of the systems that we had to come up with in order to be able to monitor what we were seeing. So let's see, current status. Well, I'll show something a little bit, just some pretty pictures here. So this is actually during some of our mock-up testing. This is before we started using real hardware. This is that granite-based stage I mentioned with the super precision THK rails. It's on this carriage. On that carriage, there's actually a load cell built in here. So there's actually a double parallel beam flexure with a load cell between it. And so when we are raising the raft up or lowering this arm down onto the raft, we actually can get feedback on how much pressure we're exerting. So for instance, when we were raising the arm up into the cryostat, we actually had software that we used for that process, a custom software application. And when we would see a 5 Newton load increase, we would stop the motion of the motors, because we were trying to limit any unwanted loads on the system, because that meant we're touching something. This is actually underneath the cryostat, so kind of give you an idea of space and the size of that raft tower module, and these little tiny threaded rods that actually attach to the RTM and up to this plate, and this is actually what was our surface that we could attach to with this big carbon fiber arm that would raise up through the cryostat. This again is our mock-up testing, and I include this picture just because it's much easier to see kind of the internals of the cryostat. The real cryostat, there's just too much stuff going on to really be able to visualize with a picture. But we can see here there's this copper color. This copper plate is what we call a cryoplate. So that is actually the surface which gets very cold during use of the camera. But it's also our mechanical interface for the Raft tower module. And so we are trying to raise up and bolt the Raft tower module to this cryoplate for both mechanical and thermal connection. And we couldn't have a lot of lost surface. So there's just a little U-cut for these four threaded rods that I mentioned that we have to in order to hold on to the Raft tower module. And then there's just a square cutout. You can see over here, there's basically just a square cutout for each of the 21 bays. Higher up in Z is this cold bar. So the cold bar is another aperture that we had to watch out for. You can see that very tight clearance to the cold bar as well. It's again about 1 millimeter of clearance between this part as it comes past this cold bar, which is part of the fixed cryostat. And that cold bar is used to remove the heat of the readout electronics. So that's there's two different thermal zones within the cryostat. There's a cryo surface that it's just minus 130, and there's a cold surface which is minus 40. And those two are used for different purposes. One is for the CCD, and the latter is for the readout electronics. This is just looking up through the bay, so you can kind of see what the Raft tower module sees as it goes up through the cryostat. There's a lot of features that I'm not going to talk about in here, but essentially some of those, that aperture that I mentioned that you have to pass through, that the Raft tower module has to pass through. A lot of hangups. These little cold heater wires that are on the sides here. We had some issues with those at one point in time. There are some thermal radiation shields that are in here, which hung over an extra millimeter into the clearance here, which caused us some problems that we had to resolve. So a lot of small details really make a big difference when you have a very tight tolerance object like this. So this is real hardware going in, and I don't think this one was ever removed. So this is a Raft tower that's being installed into the cryostat. And you can see that we already have several already installed in this image. Here's, once the Raft tower module was raised up high enough, we installed these lenses, these telecentric lenses, and turned on those cameras and fired up the software so that we could see the relative position of this sensor relative to both this one and this one, which would be the two of the edges that we really have to watch out for. And if we were able to, what we would do is bias it in this direction, raise it up as far as we could, and then slide it over a little bit, and then raise it up onto its kinematic mount. But that was not always the case. We were not always able to do that. We have these fun little Lego people here. I guess I was just being a little fun with Legos. So here is a very close-up image showing some of the details. So this is that 500 micron gap between two of the sensors. To give you an idea, these are the wire bonds that you're seeing. These gold lines are the actual wire bonds between the CCD and the backing structure for the CCD itself. And those traces obviously eventually go up to this connector up here. But in order to get there, these are the little, very, very fragile little wire bonds. Those actually were a bit of an issue at one point for us. I'll talk about at the very end. I'll talk about some of the issues we had with those exposed wire bonds. And voila! This was our grandiose final day of installing sensors into the cryostat. It was a very momentous day for us. So that was earlier this year, actually, beginning of this year. We didn't have a chance to get fully involved in the testing of the sensors before COVID shut us down. So we went through a very long period of just kind of waiting before we were able to turn on the refrigeration systems, those cryo and cold refrigeration systems, the 2 thermal zones, so that we could actually start turning on the CCDs and reading out the images. But when we were able to, finally, this was actually just last month that we started being able to read out some of those images. On the left is that Romanesco broccoli. I think that Andy sent out a picture or a link to a picture of this. And the other one is a picture of Vera Rubin from one of her library of images. So these are extremely large images. Obviously, these are just a snapped JPEG that I've included in here, but we do have a viewer that allows us to zoom in on the individual pixel level. So we actually can zoom in on individual pixel levels in our viewer. So we've got these images. The camera's done, right? Not quite. So here's our large clean room. So this clean room that we built is dedicated just for this project. It's 25 feet by 75 feet long. It has a 20-foot hook height of the frame. The ceiling itself is 26 feet high. So it seems like a very large clean room, but it is really full right now. I'm actually struggling with space. There's a lot of stuff that has to fit in here. And there's definitely some things that aren't in here yet, so we still need to get in here. So this was actually just captured a couple days ago. You can see the camera body itself is mounted on this big stand up here. This big stand allows us to rotate the camera about its axis, and then also to change its elevation angle by rotating it about an axis, a horizontal axis here. So we can actually rotate this thing so that it points down. And then we'll do that for the final testing. So once it's completely assembled, we have the big lens on there. We'll take these deck plates out from the stand. We'll rotate this camera, face it down. We'll enclose it in a dark box and put some light projectors inside that dark box to allow us to test this thing at the completed camera assembly level. So the previous pictures I was showing from the cryostat are where we actually get most of our requirements to achieve verification of most of our requirements, but there are still some that we're not able to do at that cryostat level that we have to do at the complete camera level. So, pre-COVID, we were supposed to be done January 2020 or 2021. At this point, we're going to be done with the camera assembly itself by August next year, and then we have a few months of testing before we're ready to call the project complete and get ready to ship it. So we'll be shipping sometime in December or January 2022. We've done a lot of the preliminary testing and all the mechanisms, like especially the filter exchange system and the shutter. The filter exchange system is a very complicated process because, of course, we have to hand off from one set of clamps to another set of clamps, and we don't want to drop a filter in the process. So there's a lot of checks, a lot of safety systems in place for doing that. So it makes both the mechanics of it as well as the control really complicated. So it needs a lot more testing. And unfortunately, this was a system that was designed completely by our collaborators in France, the IN2P3 National Labs, and they are not able to come to SLAC to help us. So I'm spending my very early mornings. I get in the lab at 6 o'clock in the morning, and I spend a couple hours working with them because, of course, that's the end of their day and the beginning of our day. And that's the only chance we have to coordinate some of the testing that we need to do on that system. So that's currently ongoing. All of the corrector optics, the L1, L2 pair, and the L3 are already in our clean room, so we actually have all of those. The 6 different colored filters are still going through their coding and metrology processes. have a couple of pictures just because pictures are fun, especially when you see the size and the scale of some of these things. So this is actually that L3 lens. So it has a little bit of power, but not a lot of power. It does have, so it has some shape, but it's a plano convex. It's roughly a meter in diameter for the whole lens cell. So it's a pretty large lens, and it's also our vacuum barrier. So it needs to be a very high quality piece of glass. And of course, any inclusions, any irregularities in the homogeneity of the glass really causes problems with the ability to read out the images from our sensors. I think most impressive is this L1, L2 lens assembly. This L1 is the thing that's, it's roughly 5.5 feet in diameter. It is very impressively large, and it has an incredible amount of shape to it. There's about 10 inches of convex shape on this L1 surface. And we think, nobody's told us otherwise, but we're pretty sure that this is actually the largest optical transmissive lens in the world. It's a really big piece of glass. It was very expensive. So I'm a little bit terrified about when it comes to the process of installing this on the camera, I'm not gonna lie. So it's actually two lenses. It's a pair that they're held in place with a carbon fiber structure. The carbon fiber structure was for both structural reasons as well as thermal reasons, to make sure that there's not a growth between the lens pairs when there's temperature swings. The entire assembly is adjustable on a modified hexapod. So it's not a true hexapod, but it's a hexapod that allows us to adjust the position of the lens cell like a hexapod. So it has 6 degrees of freedom. So we can set the location of the axis of this lens pair relative to the L3 and the focal plane. So that's getting all those things lined up is a very critical part of the camera assembly. So I mentioned a little bit about the filter exchange system. So this is what we call our auto changer. So it actually is what automatically changes the filters from one color to another. So what you see here is a blank. It's aluminum blank. We're not testing with real optics. But it's moving from, in this picture, it's moving from the online position, which is in front, in the center of this camera body, to it rotates up and gets stored on that this carousel assembly. So, and then a carousel is like a rotating cartridge. The reason for this, by the way, most camera systems on telescopes, when they have filter changers, the filter changer is just a series of filters in a row, and the thing's on a shuttle, and it just goes back and forth. The challenge with this particular one is that the beam line of the telescope actually comes right past the edge of the camera body here. So we can't have anything protrude beyond the diameter of the camera. So that's why this mechanism is a crazy complicated mechanism in order to be able to get that filter stored and changed out without breaking the outside diameter of the camera. This is looking the other direction. Not a whole lot interesting to see here. These big black bars here are actually part of the system for the rotating carousel system. Our shutter. So this is a very custom shutter that we designed. It had to be extremely thin, like 3 millimeters. Each blade is 3 millimeters thick, and there's the overall thickness of the shutter is like 10 millimeters, and it has to be very fast. So the blades open. It takes 1 second to open the entire aperture, and it's roughly a meter aperture for the shutter. And it has a couple different ways it can operate. So there are actually 2 sets of blades. So there's a blade right here. There's another blade right here, and those 2 can travel all the way to the opposite side and the two blades will cover and close off the opening. So, and then these two blades can come all the way back into a storage location on this side. And there are actually two blades on the opposite side, and they also can go all the way across and close off the aperture. And the reason for that is that one of the requirements is that we have the ability to have a traveling slit, traveling opening slit of this thing. So the four blades together can move coordinated so that there's a very narrow slit that travels across the focal plane. And we do that in case there are extremely bright objects, which are too bright, and we want to minimize how much light gets integrated onto the CCD surfaces. All right, so lessons learned so far, I guess. We do a lot of planning in our group, in our integration and testing group. We do a lot of planning. I didn't show a whole lot of the slides that I had originally intended to show for all the planning stuff. But plans are great, but they have a tendency to go awry almost as soon as you start to act on them. So really, it's not if things go wrong; it's really when. So being really adaptable on a project like this has been really key because we don't have the ability to do a whole bunch of testing on each system. We're building one thing. We're not building 20 of them. We're not building 100 of them. And when you're building a single thing, you plan and you do analysis, and then stuff goes wrong, and you have to figure out how to fix it on the spot. Cleanliness has been a really big issue for us, especially inside the cryostat. So those sensors, those CCD sensors, have those exposed wire bonds that I mentioned on that perimeter, and we had a big issue with particulates, especially metallic particulates, bridging across those wire bonds. And when you have a short across some of those wire bonds, it basically fries not just the sensor, but can also damage the readout electronics board as well. So it was a really big problem for us. We ended up tearing apart, disassembling every one of those Raft tower modules. We redesigned all the fastener connections because we determined that was actually what was causing a lot of the issues for us, the threads. So bare copper with stainless steel was generating a lot of particles. So we put in inserts. We changed the material of the screws to like Nitronic 60, that sort of thing. And then we reassembled everything after the parts were modified, and we re-cleaned every single surface. And we hope that we have no issues with this again, and we have not yet. So we think that solved our problems. But really the point is the cleanliness needs to be, for a system like this, it really needs to be involved in both the design as well as all the processes. So your procedures that you come up with as well as the design. And incorporate it very early on. Don't wait until it's too late like we did. Sensors are really fragile, turns out. This was a really unfortunate event. This sensor it got bumped by a camera lens. We were trying to image something else, and the person who was taking a picture just had a very brief lapse in paying attention, and it bumped the edge of the sensor, and obviously you can see that it chipped it, and you can see those wire bonds in fact are what's holding these pieces of silicon. So the silicon of this sensor is 100 microns thick, so it's a really thin sensor, and the very last millimeter of the sensor is completely exposed. There's no backing on it, so it's just hanging in the wind. So it doesn't take much of any force to crack that silicon. So unfortunately, this was about 3/4 of the way to a complete focal plane array. So we had to take this Raft tower module out of the cryostat, We had to disassemble it to remove this sensor and replace that sensor. And these are about 150 grand a piece. So they're a very custom CCD made just for this project. So it was unfortunate. It didn't ultimately cost too much for us to do this in time and schedule and cost. Obviously, replacing the sensor, we already had a spare sensor, so it was already purchased. But it was one of those things that nobody wanted to do, and nobody wanted to be the person responsible for that, and it's just a little bit unfortunate. One of the things I guess I'll mention is I think I alluded to it in the abstract is the screws. So inside of our cryostat, we have a lot of fastener connections. I mean, a lot of fastener connections. So making sure that all of our procedures had good ways of holding on to fasteners was really important, as was the design of a lot of these things. So we designed almost all of these fasteners to be captive so that we didn't have to worry about losing anything inside of our cryostat. One instance, unfortunately, this is an Omnetics micro D connector. It's a 37 pin. It's a pretty small connector, high density. This is where we fed all the power to our Raft tower modules. These screws on the two sides, these are a number 256. They're a really small screw. And we designed it so that the washer, which was threaded, so the washer is actually threaded onto the screw, and that was intended to keep the screw captive on this connector. Unfortunately, these washers unthreaded themselves pretty easily, and in the process of installing these cables into our cryostat, we had a few of them fall off. So we lost both the screw and the washer on a few of them. And there was one washer which we never did locate. We're not sure where it is. I certainly hope that it's outside the cryostat somewhere on the floor, and we just never found it. And we'll find it when we clean up the clean room in the end of next year. But it's one of these things which was on the watch list at the DOE headquarters for a long time, and remains so because it is a potential issue. So this is one of those things where we did think about it. We thought about how to mitigate the issue of keeping a screw captive in the system, and unfortunately, didn't do enough. We didn't do any testing of how what the efficacy of that design was, and it ended up being a problem for us. So for some of these things, it's design, but then also the whole FMEA that you need to do to make sure that you're not going to end up with some problem with your design process. And that's all I had. I guess I went a little over time, but I have there's a lot more slides, but I'll end the discussion at this point and open it up to Nate to field questions.
Thank you, Travis. That's really great. Let's give him a quick round of applause, everybody. I know it's a quiet applause. I guess we have either the icons or we can see each other applauding. But I think I'll open the floor up for Q&A. And I think it looked like Chris had a question here in the chat. Chris, do you want to ask your question? I'll ask it for him. Sorry, oh, he doesn't have a mic, thanks. Given the clearances that you need to install those CCD modules, was it difficult to diagnose any issues with the tolerances as you were going along? I mean, because you can't really look inside those enclosures. I know you kind of talked about some of those clever light shining through cracks techniques that you guys developed, but were there any others?
Yeah, so that actually is a huge issue, because you're right, it's a ship in a bottle problem. And you do not have any ability to see inside the depths of the cryostat. Once the raft is inside of that bay of the cryostat, you're just totally blind. There wasn't really a way for us to get down inside internally it kind of required us to kind of have an understanding of the design and just say, okay, I think it's this thing is bumping into this particular thing, and then we'd remove, you know, the raft tower from the bay, and then go in and look. And like I said, I think I pointed out some of those little coiled up wires. Those were a problem. Some of the shields, those were a problem. And just the process was unfortunately a little bit empirical and not as much a design layout as we would like it to be.
We have another question from Alan. Alan, I guess if Alan wants to unmute himself. Or I'll ask it, I guess. So once up and running, how do you control dust from getting inside the instrument? I know you built it in a clean room, but it can't live in there forever.
Right, yeah, so obviously inside the cryostat will never be opened again, right? So, you know, we did a lot to make sure that stayed really clean when we were building the cryostat. So we hope that that's never going to be an issue. I mean, there are some particulates inside there. If there are, we just hope that they don't migrate, right? If they're fixed onto a lens surface, that's not a problem. It's when they move that's a problem. Externally, on the camera system, dust. So we have, I'll tell you a couple of different things. One is we actually have a purge air system. So it's actually it's air conditioning with filtration inside the camera body. So back in that utility trunk of the camera. So back in the utility trunk, there are some forced air systems that have both, you know, temperature control of the air as well as the velocity of the air, and then there are filtration. So filtration for humidity and particulates, and that system forces air. There's a couple different systems actually. So one forces air through the mechanisms, so the things that have motors. There's one system that forces air through those motors. There's another system that forces air just through this big volume of space inside the camera, which is completely sealed up. It's totally hermetically sealed. So it's all, you know, there's foam seals or, you know, or O-ring seals on every surface of this camera. Obviously, externally, this thing is going to be hanging out inside of a dome. You know, there's birds, there's dust, there's all kinds of stuff inside of a telescope dome. So the external surfaces will get dirty. There's no doubt about that. You know, if and when we have to do maintenance on a camera, we remove it from the telescope, we bring it down into a maintenance area at the summit, and we'll literally wash down the exterior surface. There is a wash station at the summit, and it's meant for all the mirrors too. So the very large mirrors, you know, the 8 meter mirror, as well as the secondary mirror, they both are going to have to be recoated at some point. So there is a wash station on the summit to be able to clean those optics. So that we would use the same wash station to clean the exterior of the camera before we start opening it up and taking it apart, right? So that we don't introduce a whole bunch of stuff into it. But if we do, we have those internal systems to deal with some of the particulates in the volume of this camera, as well as, you know, getting the heat and particulates out of the mechanisms too.
Thanks. I think you, Chaman had a follow-up question on that, and I apologize to everybody else. I had disabled the unmute feature, so you can now unmute yourselves. I took off that little security, but I think that kind of answered Chaman's question. But Chaman, did that address your question about cleaning? Okay, he says yes. All right, great. Kevin has a couple questions. Kevin, do you want to ask your questions if you're still there?
Sure. So my first one was basically, did you have somebody trained to move those Raft towers? Like, how, I can just imagine, you know, doctors, surgeons have to like train by suturing grapes. Did you have somebody like playing video games in the background to move those? And then the second question was, the feedback from those 4 cameras pointing at the sensor corners, was that feedback just visual, or did it run through your software to kind of guide the motion?
Yeah, so I'll address the first one. The first one, you know, was the actual process of installing the rafts. we did a lot of practice. So we actually built 5 Raft tower modules with non-functioning CCDs so that we could do a lot of testing. So we didn't have to worry about damaging them. And we built a non-functional cryostat as well. So we practiced putting those mechanical rafts into our mock-up cryostat. That's actually what this image was showing, is that this is our actual mock-up of the cryostat, of just the critical features, not of the entire cryostat. So we could really test out and vet the process a lot. And then we had a dedicated team of people. So, I was kind of overseeing the whole procedure, all the process. And I had somebody who was driving the motors that raised the raft tower up and down, as well as side to side, and front, back, left, right. There was somebody dedicated underneath to watch everything that was happening with the raft tower underneath. There was somebody mounted up on top of that big weldment where the cryostat was installed, and that person was watching down from the top down through the bay. And then lastly, we had one of our scientists who actually came up with the software for monitoring those the feedback from those four cameras. So we had those 4 cameras. So that was basically the team. So we did a lot of practice with that same team. We used the same team for all the practice runs that we used for installing the 21 science rafts and 4 corner rafts. So that was basically the process that we went through there, as far as specific people. So it wasn't automatic. It was mechanical controlled devices with human intervention. I'll say it that way. We needed the human intervention. There's no way we were going to do that without. Sorry, I don't have any other good pictures. So I don't have the pictures which show the actual what the images of this look like. So we had some software that we actually designed. Like I said, our scientists actually wrote the software that was reading out these 4 corners. So we were looking at those images, and then using the software to actually measure what the real gap was between the sensor we were installing and the one that was already installed. And I guess I didn't even mention, the reason for us to have the telecentric lenses, which was very important, is that the depth of field of when it would be an issue for this sensor being installed relative to the one that was already installed was something like 40 millimeters. It's really hard to find something that doesn't give you parallax over that range of depth of field. So that's a real issue when you're trying to measure direct line of sight like this. So the telecentric lenses that we did find had enough depth of field for us. Unfortunately, it meant their magnification was really terrible, because unfortunately those go inversion ratio. But yeah, so we came up with software that actually told us what that gap was, and so we had somebody constantly monitoring that clearance. And so we'd raise up the raft, we'd stop, we'd say what's the clearance, and then we decide how much it needs to move in what direction, and we'd move it a little bit, and then we'd raise it up. And we had in our procedure, I mean, we did, like I said, we did 21 of these. This is one of the few things on the entire camera where we had enough of them that it was a bit of production, right? So we actually could take the time to really procedurize this process of getting the rafts installed. So we did enough times. We constantly evolved the process. We had set points in the vertical direction. We had very dedicated set points where we would stop, we would inspect, we would move things left, right, before we went on to raising things further. So I think I covered that question, Kevin. If I didn't,
yeah. He says thanks. I guess maybe if anyone else has a question, if they want to ask in the chat or unmute themselves.
How do you do the cleaning of electronic cleaning of the camera and sensors? I see one from Shaman.
Yeah, that's the one that I think you kind of touched on that. In terms
Yeah,
of,
we don't touch the sensors after they're installed. We did do a cleaning right before we installed them. So we actually had a single hairbrush, a single horsehair brush, with a fiber optic camera, and we would go across the sensor and detect individual pieces of dust and try to remove them with a single horsehair brush. Just because we don't want to do anything that's going to cause any scratches, because these things have some AR coating on the surface of the sensors, and we don't know exactly what that AR coating is. It was proprietary. They didn't tell us exactly what the AR coating was. We just gave them just a spec, and they met it. So we didn't want to chance scratching those things, because any type of scratch you're going to see at some point in the different images.
well, thank you very much, Travis, for this great talk for everybody. And on behalf of our audience, I want to give you another round of applause as well, and let everybody know that we've got additional seminars coming up following this one too. So next week, we have an additional seminar for mechanical engineering for space.
Awesome. You know what? Thank you for the invitation. I appreciate it. That was very fun to present to you guys.
Thank you so much.
All right. Cheers.
Cheers.